We're going to continue looking at the algebra of functions, and we're also going to look at the domains and ranges of functions when functions are divided by one another, or if we're involving a square root or anything along those lines. And so that's what we're going to take a look at next, is the domain of functions when they involve division, fractions, and square roots. So just a little side note. When we think about functions, just a reminder that the domain is our input values or x values that go into the function and get evaluated. The domain of a function is all real numbers, so from negative infinity to infinity, unless there is a fraction or a square root. So what happens if we have a fraction is that we have to avoid the values of x, which make the denominator 0. So we have to set the denominator equal to 0 and solve for x. To figure out when is x equal to 0, or when is the denominator equal to 0, and when it's equal to 0, it cannot be contained in the domain because it would be undefined at that point. The second stipulation is that if we have a square root value, we want to only include values of x that result in a positive number under the square root symbol. So in this case, we take whatever's in the radicand, or under the radicand, or under the radical sign, and we set that to be greater than or equal to 0. So I'm going to write raddy, for radicand, has to be greater than or equal to 0. These are the tools that we're going to use to help us determine the domains of different functions. So for this first example here, we're finding the domain of each of the following functions. And the first function is f of x equals 3x plus 7. So what I need to check is there a fraction that has an x value in the denominator? No, this is just a linear function. There is no fraction in the denominator that has an x value. Do I have any square roots? Nope. So in this case, my domain, D, is from negative infinity to infinity. All right, let's look at the next one, g of x. We have 1 over x minus 3. This function is a fraction. We have 1 over an x value of some sort. So what we have to do is we have to find out what values are not allowed in the domain, which values would not be defined in the real number system. And so I take my denominator, x minus 3, set it equal to 0, and solve for x. Add 3 to both sides. And I get that x equals 3. So when x equals 3, the function is undefined. So that means that this value is not in the domain. So therefore, my domain for this function would be negative infinity to 3. It does not include 3, union with 3 to positive infinity. So that's my domain for the second example. The third example, g of x equals the square root of 9x minus 27. The square root can only be evaluated when what's under it is positive. It gives us a positive number. So what we do is we take that 9x minus 27 and we set it to be greater than or equal to 0. I'm going to add the 27 to both sides. So I get 9x is greater than or equal to 27. Divide both sides by 9. Because 9 is a positive number, that won't change our inequality sign. So I get that x must be greater than or equal to 3 in order for this to be true. So therefore, my domain for this function has to start at 3, including 3, because my inequality sign includes that value itself. Here, I'll circle it down there. And it goes all the way to positive infinity because it's all the x values that are greater than or equal to 3. So that would go upwards towards positive infinity. Before we go on, I want to do a quick crash course, going to throw back to factoring. We're going to factor some polynomials 2 different ways. The first way is I have a trinomial here. We have x squared minus 3x minus 18. If you recall, when you factor polynomials, you're looking for 2 numbers that multiply to get the last number and add to get the middle coefficient. So what are my factors of 18? I have 1 and 18, 2 and 9, 3 and 6. And so out of these options, what pair could get me a negative 3? That's going to be this one. And I have to determine which one of these is positive and which one's negative, because this is a negative 18. But I also want to end up with a negative 3 here. So if I have positive 3 and negative 6, they will multiply to get negative 18, and then when you sum them together, you get negative 3. So this factors to x plus 3, x minus 6. The reason why factoring is really important is because when we have numbers in the denominator or factors in the denominator that can cancel with the numerator, we end up getting what's called a whole, but it's allowed to occur. We're still allowed to include that value in our domain because it cancels out. We'll talk more about wholes when we look at graphs of rational functions in a later time. But anyway, we want to be able to factor polynomials so that I can factor denominators and numerators and figure out if anything cancels. So let me also factor out this one, x squared minus 81. What this means is that my middle term, you could think of this as being x squared plus 0x minus 81. So what ends up happening is we're looking for the factors of negative 81 that would give me 0 when they sum together. So my factors of 81, I have 1 and 81, 3 and 27, and 9 times 9. And remember, because this is negative, one of those values would be positive, one of them would be negative. So the only way I can get 0 is if I have a positive 9 and a negative 9. So this binomial factors to x plus 9, x minus 9. This is one of those special cases. It's one of the special cases of factoring binomials or factoring trinomials. In this case, it's a binomial. It's a special case because when I multiply out those factors, the middle term cancels. On this last green example, I'm going to factor twice. The first thing I can do here is I can factor out a 2. I get x squared plus 2x plus 1. That's called factoring out a greatest common factor. Then I'm looking for 2 numbers that multiply to get 1 and add to get positive 2. So that's going to be x plus 1, x plus 1. And I still have that 2 on the outside. So this fully factors to 2x plus 1 squared. Okay, now I could write it out as x plus 1 times x plus 1. Sometimes that's easier to see when things will cancel. But anyway, this is a very important, helpful tool when you can check to see does anything factor out of our denominators and numerators. So let's find the domains of each of these functions below. Now remember, the function will be from negative infinity to positive infinity unless it is written as a fraction form and is a rational function, or if it has square roots. And so we have to keep that in mind. So here we're going to look at this first one, f of x equals 5x over x squared minus 49. We want to factor out that denominator just in case something did cancel out. And in this case, we end up with 5x over x minus 7, x plus 7. Nothing factors out, and so therefore in this case we can take each of the terms of the denominator and set them equal to 0. X minus 7 equals 0, x plus 7 equals 0, because we're looking for when is my denominator equal to 0, and 0 times anything equals 0, and so if this term equals 0, then the denominator is 0, and also if this term is set equal to 0, then our denominator is equal to 0. So I'm going to solve each of these, and I get that x cannot equal 7, and x cannot equal -7. So our domain for this function right here, I'm going to write it in purple right above it, is going to be from -infinity to -7, because we're going to have a break there, unioned with -7 to +7, because that's when we have our next break, union with from 7 to infinity. Now notice that I use curved parentheses and not brackets, because 7 is not included, and -7 is not included in our domain for this function. So this, in boxed in purple, is our domain for example D. Example H, we have no fraction value, like no rational function with a numerator and denominator where there's x's involved. There's also no square root. So the domain for the second example is from -infinity to +infinity. The third example is tricky. This F example, where we have h of x equals the square root of x plus 2 over x minus 7, because we have to check both things. My denominator cannot equal 0. So I have to set it equal to 0 to find out what x values make it be 0 and then exclude those. So this is the first thing we have to check. The second thing we have to check is that my square root cannot be taken over a negative value. So I also have to check and make sure that x plus 2 is greater than or equal to 0. And then we're essentially finding the intersections of both of those things. So what numbers correspond to both situations? So let's solve each of these. So x cannot be equal to +7, and x must be greater than or equal to -2. So in this case, my domain for this function is going to be from -2 to 7. It includes -2 because of this inequality sign. It does not include 7 because 7 is not allowed. It's not in the domain because it is undefined. It creates an undefined fraction. So because it's undefined, it's not in our domain. Then we are going to pick back up from 7 and go on to infinity. Again, this happens because our x values can be greater than or equal to -2 because of the constraints placed on the square root value, but it cannot be equal to 7 because of the constraints on the denominator. And so therefore, that puts limitations on the domain for this function. So let's apply this to a situation where we're subtracting two functions from one another and evaluating the domain. So we're evaluating and writing the domain in interval notation for r minus t of x. So r is given as x squared plus 3. And then t is equal to x plus 4. So when I subtract those, we can distribute this negation to both terms inside the parentheses. So we get that x squared plus 3 minus x minus 4. And so that becomes x squared minus x minus 1. And the domain for this function, since there's not a fraction and there's not a square root, would be from -infinity to infinity. Let's do some prep practice to cancel out some information from a numerator and denominator based on factoring before we move on. Just a little bit of practice for our brains. We're going to simplify each fraction if we can. So the way we do that is we can try and factor out information and see if it will cancel. So I have 2x squared plus x divided by x to the third. In the numerator, both terms have an x value, so I can factor out the highest power of x that they both share, which is x to the first. So that would leave 2x plus 1. and then that's over x squared, sorry, x cubed, and then one of the x's, that one x in the numerator can cancel with one of the x's in the denominator. So this simplifies to 2x plus 1 over x squared. Okay, the second one cannot, this one cannot be simplified. A common mistake that people try to make is they say, oh, I see an x in the numerator, x in the denominator. You cannot do that because the x in the numerator is not its own term. I can only, if I had something like this, x and then 2x plus 4 over x, this x would be its own term and it could cancel with the x in the denominator. However, in the example that we have, this x is connected to a coefficient of 2. And so therefore it's connected by addition to this term 4. And so therefore I cannot factor it out. This whole term could only factor out entirely or cancel out entirely if it matched exactly the denominator. This term essentially would cancel out with that term. That is not what is happening in this situation. In this last example, we have 5x divided by 15x plus 30. So what I can do is in the denominator, I can factor out a 5 from each of those terms, which will leave me 5 times 3x plus 6. And then the numerator has 5x. Because I essentially have 5 times x and 5 times something else, the 5's can cancel. They're not combined together with plus or minus, so they are able to fully cancel there, which leaves us with x over 3x plus 6. So looking back at the one before, it's not just the fact that the x was connected to the 2, it's the fact that it's connected to the 4 by addition. That's why I cannot cancel out those x's. That will not work, okay? But here, because these are being multiplied together, I can divide out by a common factor of 5. 5 divided by 5 is 1, so I'm left with 1x over 3x plus 6. So let's see why this is important. Using these same functions from above, we're going to do r divided by t. So r is equal to x squared plus 3, and t is equal to x plus 4. And we're trying to find and write the domain in interval notation. What I'm looking for here is, can anything simplify? Nothing factors out of the numerator, nothing factors out of the denominator's terms, and so therefore I have to look at the entire numerator and see if it can cancel with the denominator, which it cannot. These are connected with addition, so I cannot cancel them out. And so therefore, what I need to find out is, when is my denominator equal to 0? Because then I can't use that value in the domain. So I set x plus 4 equal to 0 and solve for x. X equals negative 4. So my domain for this function is from negative infinity to negative 4, and then from negative 4 to infinity. That is unioned together. Okay. Are we ready for the next one? How do I multiply two functions together? Just like when we have fractions being multiplied together, we do numerator times numerator, denominator times denominator. We can also always rewrite a number as a fraction by putting it over the number 1. So 5 is the same thing as 5 over 1. So I could say x is the same thing as x over 1. I could write the expression 2x minus 3 over 1 to make it a fraction. And that's helpful when you're multiplying a non-fraction function times a fractional function. So multiply the following: x over 5 times 2x plus 3 over 2. I can multiply this out. That's going to be x times 2x plus 3 over 5 times 2. That's going to be 2x squared plus 3x over 10. I multiply the numerators together and I multiply the denominators together. When I multiply the x times these terms, I have to distribute it to each of those terms. Okay, nothing cancels. That's all I can do with that. So this is important because we're going to try and see what happens with s times t. So s is 2 divided by x, and t is x plus 4. So that's equal to 2 divided by x times x plus 4. Now remember, I can say x plus 4 over 1 to make it a fraction. I can multiply the numerators together, which is going to be 2x plus 4 over x times 1, which equals, distribute the top, 2x plus 8 divided by x. Now, the x will not cancel because the 2x plus 8 is connected to the plus 8 by addition, so the terms cannot cancel. So essentially, I need to determine the domain by figuring out when is that denominator equal to 0. So I set the denominator equal to 0. X equals 0 is when the denominator is equal to 0. So the domain for this function here is from negative infinity to 0, unioned with 0 to infinity. I'm going to go ahead and wrap up this part 2 video on the algebra of functions. The next video is going to cover the difference quotient between two functions, which has applications in the future if you take calculus. So it's an important concept to understand now and to be able to evaluate it. But also we're going to look at composing functions with one another in the next video. So please make sure you watch that as well. Thank you.